Have you ever wondered how physicists actually sit down and model the chaotic flow of turbulent water? Or like how Wall Street quantitative analysts price complex options in a market that is just completely unpredictable?
Right, because by its very nature, the market is just chaos.
Exactly. So, welcome to this deep dive into a really mind-bending exploration of mathematics. We are venturing into a place where the classical rules of the universe just completely break down.
It really is a fundamentally different universe.
It is. It's a place where the smooth, predictable curves you might, remember from high school or college calculus are entirely replaced by these jagged, erratic, totally unpredictable paths.
And that's a hard pivot for a lot of people.
Yeah.
Because when we learn basic calculus, the kind Isaac Newton and Leibniz developed centuries ago to track planets and falling apples, we are taught a very specific philosophy.
Which is that nature is smooth. Right.
Exactly. We learn that if you zoom in close enough on any curve, no matter how steep or winding it is, it eventually flattens out into a straight line.
A tangent line.
Right, a tangent line. But in this deep dive, we are looking at systems where that philosophy entirely fails.
Because what happens when you zoom in on a line and it just never becomes straight?
Yeah, what if it just gets violently more jagged the closer you look? Like it
Oh.
reveals this fractal of infinite chaos.
So our mission today, for you listening, is to decode exactly how mathematicians manage to tame that pure randomness.
It's a heavy topic for sure.
It's notoriously heavy. We're tackling a really dense masterclass level dialogue on stochastic differential equations, or SDEs, and the completely alien world of Ito calculus.
But the underlying logic is just a fascinating story of mathematical accounting. We're basically looking at how human beings realized their classical tools were broken, and rather than just giving up, they engineered this entirely new scaffolding to measure the unmeasurable.
To harness chaos, put it in a box, and actually use it to predict the real world.
Yeah, we are essentially trying to measure a system that is actively resisting measurement.
Which is wild. So here's the blueprint for how we're going to tackle this. We'll start from the ground up by untangling a classic one-dimensional random process, the Ornstein-Uhlenbeck process.
Then we're going to zoom in and look under the microscope at this bizarre paradox involving the speed of time versus the speed of randomness.
Right. And from there, we'll scale all the way up to infinite dimensional random fields and finally discover why the fundamental concept of a derivative actually dies when exposed to pure randomness.
It literally ceases to exist.
Okay, so let's jump right in. Before we can run, we have to walk.
Right.
The source material starts with this brilliant foundational question that really tests our basic assumptions. It introduces the Ornstein-Uhlenbeck process.
Which is a very classic stochastic differential equation.
Let me just spell the equation out for you listening so we can picture it. It's written like this. Do equals negative gamma u dt plus sigma dx.
That's the one.
So let me make sure I'm visualizing these letters correctly just to be safe. We have a do on the left side, which is the change in our system, right?
Correct. The infinitesimal change in the state.
Okay, and on the right, we have a dt term, which stands for a tiny step in time, and then a dx term, which is a tiny step in randomness.
Yeah, usually representing Brownian motion.
Right. So the text poses a question about this equation. When you look at it, is it a one-dimensional equation or is it a two-dimensional equation?
Which is a bit of a trick question.
It is, because intuitively, looking at the right side, I see two distinct variables driving the change.
You see the dt and the dx?
Yeah, I see dt pushing things forward in time, and I see ds pushing things around with randomness. So it feels like a two-dimensional grid, like time is the x-axis and randomness is the y-axis.
It is a very natural assumption to make, especially because our brains are basically trained to see two different letters and immediately assume they represent two different spatial directions.
Right.
Well, to understand the mechanics of why, we have to rigidly establish the difference between an independent variable and a dependent variable in this specific context.
Let's break that down because I think people get those mixed up. In my head, an independent variable is the input. It's the thing that moves on its own regardless of what else is happening.
That is an excellent definition. So in this equation, the sole independent variable, the only thing that is marching forward free of any outside influence, is time.
That's our t.
That is our t. And the dependent variable is u, which represents the state of the system, written as u of t.
So if we use like a physical analogy, time is the single unbending train track stretching out into the distance, and u is the train moving along that single track.
I like that. Now apply that analogy to the random dx term. The mistake people make is thinking that x represents a separate spatial dimension.
Like an entirely new set of tracks branching off to the side.
Right, like a track you can drive down. But it's not. dx is merely a random perturbation. It's a shock occurring strictly along that single timeline.
Oh, I see. So the train is locked on the single track of time, but the suspension is just totally shot.
Yeah.
As it moves forward, it's violently vibrating and rattling up and down on the rails. But the rattle isn't a new dimension I can steer the train into. It's just noise happening to the train as time drags it forward.
That captures the physical intuition beautifully. The state of the train, RU, changes based on two forces acting simultaneously along that track.
Okay, what are they?
First, you have a predictable trend, which the equation calls the drift term. That's the negative gamma UDT.
Which is basically deterministic friction, right?
Exactly. If there were no randomness, the train would just smoothly glide to a halt because of this term, pulling it back to the center.
But the real world is messy.
Right. So second, you have the random fluctuation,
Mm-hmm.
the diffusion term, which is sigma dx,
The rattle.
the rattle. This represents the random potholes or wind gusts hitting the system at every microscopic instant of time.
Okay, but I want to push back a little here on behalf of you listening. Because if X, this random Brownian motion, is just a vibration happening over time,
Yeah.
doesn't that mean dx is fundamentally just a fancy version of dt? Like the vibration only exists because time is passing.
Oh, I see where you're going.
So couldn't we just treat dx as a derivative of time, like a function of dt?
You are falling into the absolute ultimate trap of classical calculus right now.
Am I?
Yes. And it is exactly the intuition that the source material spends pages tearing down. This assumption that you can just absorb dx into dt because they both unfold over the same timeline is completely wrong in stochastic calculus.
Well, wait, why? If they're both happening on the exact same train track, why don't they play by the same mathematical rule?
Because they operate on entirely different mathematical scales. They might be riding the same train track, but they are experiencing the passage of reality at completely different speeds.
Different speeds.
Yes, and this severe speed difference is what eventually forces us to rewrite the foundational laws of multiplication and derivatives.
Okay, you're going to have to prove that to me.
I will. To prove why this random term, gx, outpaces time, our source text tells us we have to zoom in.
Put it under the microscope.
Exactly. We need to look at how these elements behave at the infinitesimal level, what the text calls the microscopic battle between dt and dx.
Okay, let's look at Brownian motion, our x, under that
So
microscope.
it has a property that drives classical mathematicians to absolute despair. It is continuous, meaning the path never breaks or teleports from one place to another,
What's it?
a vertigraph, but it is nowhere differentiable.
Nowhere differentiable. Okay, let's translate that for a second. In calculus, differentiating something means finding its slope, right? Or its exact speed at a specific point.
Correct.
So if it's nowhere differentiable, it means no matter how far I zoom in on the curve, the line never smooths out. It's a fractal of pure jaggedness.
You can never draw a clean tangent line to it, ever.
Which means you can never calculate its exact speed at any given instant.
Exactly. And the root cause of this infinite jaggedness comes down to what the text refers to as the variation scale.
The variation scale. This is the core mathematical proof of the speed difference, right?
Yes. Let's imagine a macroscopic chunk of time. We'll call it delta t. If you wait for a time increment of delta t, the time that has passed scales proportionally. It's a linear one-to-one relationship.
Sure, if I wait 10 seconds, my stopwatch shows 10 seconds.
But random increments, the mixed macroscopic delta x, do not scale linearly with time. According to the statistical properties of a random walk, the distance you travel from your starting point scales with the square root of time.
Wait, let's stop and look at the mechanics of that. Why the square root?
Imagine flipping a coin every second. You take a step forward for heads and a step backward for tails.
Okay, I'm walking back and forth.
Over time, your average position will be right where you started because the lefts and rights cancel out. But your variance, the measure of how spread out the possible outcomes are, grows linearly with every single flip. Every second that passes adds more uncertainty to where you might end up.
Okay, I follow that.
And since standard deviation is the square root of variance, the typical distance you can expect to wander from the center scales with the square root of time.
Okay, so the random spread is tethered to the square root of delta t.
Precisely.
Let's push this to the extreme limits like the source material does. What happens as our chunk of time gets microscopic?
As delta t shrinks towards zero, becoming our infinitesimal dt, we have to look at the ratio between the random step, in the time step, you are comparing a tiny number, dt, to its square root.
Let's use real numbers. If dt is a small fraction like, say, 1/10,000th,
Then its square root is 100th.
and 1/100th is massively larger than 1/10,000th, it's 100 times bigger.
You see the problem immediately. The smaller the time interval gets, the relatively larger the random fluctuation becomes compared to the time passed. As you approach the absolute limit of 0, the random fluctuation dx becomes vastly larger and infinitely faster than the slow passage of time dt.
Because the square root shrinks so much slower than the raw number.
Exactly. You cannot divide dx by dt to find a speed, because you are dividing a massive relative number by an infinitesimally tiny one. The math literally explodes to infinity.
So if I try to use an analogy here, it's like comparing the slow, steady flow of a river, which is our dt,
Okay.
to the hyperactive jitter of a water bug on the surface of the river, which is our dx.
That's a great visual.
If I try to calculate the bug's speed by dividing its jagged, instantaneous movement by the river's slow forward flow, the classical math just shatters. From the perspective of the creeping river, the bug is effectively teleporting back and forth at infinite speed.
That is a highly accurate way to visualize it. And because of this extreme difference in scale, the mathematical rules for multiplying these microscopic elements change entirely. Well, in classical calculus, if you multiply a tiny time step by another tiny time step, if you calculate dt squared, the number becomes so incomprehensibly small that mathematicians just throw it away.
It rounds down to 0, and we ignore it. Like, if you square 1/1,000,000th, you get 1/1,000,000,000th. It vanishes from the physical reality of the equation.
Right, but in stochastic calculus, we use a framework called Ito's isometry. And this gives us an entirely new multiplication table.
Because the scale of dx is fundamentally tied to the square root of dt.
Yes. So what happens when you square the random term? What happens when you calculate dx squared?
Well, let's think about it. If dx behaves like the square root of dt, then squaring it is just squaring a square root.
And what does that do?
They cancel out. You are left with just dt.
You are left with exactly dt.
Yeah.
The equation dx squared equals dt is the absolute cornerstone of the entire field of stochastic calculus.
I need to pause on that because it sounds profound. You're saying the chaos, when multiplied by itself, crystallizes into standard predictable time.
It is profound. Classical calculus multiplication rules are permanently altered here. When two random microelements multiply, they don't vanish into 0 like classical microelements.
They survive.
They generate a first-order time element, they survive the zoom-in process, and they forcefully push the system forward.
That is wild.
This mathematical phenomenon, the survival of the squared random term, is literally the bedrock of asset pricing in finance. It's why volatility actually drives value in an options contract.
Okay, but this creates a massive practical problem, doesn't it?
It creates several.
We've established the alien rules of this universe. Randomness outpaces time, and squaring chaos produces time. But how do we actually solve an equation like the Ornstein-Allenbeck process we started with?
That is the big question.
If the rules of calculus are broken, how do we find a solution for it?
We use a derivation that seems to magically obey classical calculus, but only because of a very specific structural loophole.
A loophole. I love loopholes.
The source text outlines a technique called the integrating factor method.
Walk us through the mechanics of this method. Let's see if we can spot the loophole.
Okay, so to solve the equation, we first organize it. We take our original equation and move all the u terms to the left side.
So we have do plus gamma u dt on the left.
And we leave the random part, the sigma dx, isolated on the right.
Makes sense.
To solve this, we multiply both sides of the entire equation by a specific exponential function, e to the power of gamma t. This is our integrating factor.
Why that specific exponential function?
Because in classical calculus, multiplying by e to the power of gamma t creates a scenario where the left side of our equation perfectly collapses into a single clean derivative.
It becomes the exact derivative of the product, right?
Yeah.
U times e to the gamma t.
Exactly.
I remember this from calculus. It's the product rule in reverse. You take a messy expanded equation and pack it neatly back into a single box.
But here is the massive trap. We are not in classical calculus anymore.
Oh.
According to the 2D Ito lemma, which is the fundamental rulebook for stochastic calculus when you expand or collapse a function involving random variables, you can't just use the standard product rule.
Because of the chaos.
You must include a second-order correction term.
This goes back to what we just talked about. Because dx squared survives and turns into dt, We can't just throw away the squared terms like Newton did.
Exactly. The randomness is too big to ignore.
So Ito's lemma forces us to account for it.
Precisely. Ito's lemma dictates that to find the true differential of a function, you must add a term that involves taking the second partial derivative of your function with respect to your random variable and multiplying it by the variance.
Okay, that sounds intense.
The formula demands we add a term that looks like 1/2 times the second partial derivative of our function times the squared random change.
But looking at the source text derivation for the Ornstein-Uhlenbeck process, this big messy correction term isn't there. It completely vanishes.
It does.
How, if Ito's lemma rigidly demands it be there to account for the surviving chaos, how do they just ignore it?
Let's look closely at the specific function we packed into our box. Our function is u times e to the gamma t.
Okay.
The Ito correction term requires us to find the second derivative of this function, specifically with respect to u.
Let's do the math live. The first derivative with respect to, well, since it's just e to the power of 1, the u drops out, leaving just the constant attached to it, which is e to the gamma t.
Correct. Now, the formula demands the second derivative.
Yeah.
So take the derivative of e to the gamma t with respect to u.
There is no u left in that expression.
Exactly.
From the perspective of u, e to the gamma t is just a flat number, and the derivative of a constant is 0.
And there is your loophole. The second partial derivative is exactly 0.
Wow.
This happens because the original function is linear with respect to u. Because that specific derivative is 0, the entire chaotic Ito correction term, that complicated requirement to add 1/2 times the second derivative times the variance, it vanishes entirely.
Because it multiplies by 0.
Yes.
So it's not that we ignored the rule, it's that the rule asked us to measure the curvature of our function, and since our function was a straight line with respect to the curvature was 0.
Right.
The math looks like it's playing by classical Newton-era rules, but only because the chaotic penalty conveniently zeroed itself out.
It is profound convenience of linearity. If our equation had a u squared or u cubed in it, the second derivative wouldn't be 0.
The curvature would be real.
The Ito correction term would survive.
Yeah.
And if you tried to use the classic product rule, your answer would be catastrophically wrong. But here, the linear nature of the Ornstein-Uhlenbeck process saves us from the chaos.
Okay, so we've neatly packed the left side of the equation into a single differential without violating any stochastic laws. What are the final steps to actually get the solution?
The standard protocol is to integrate both sides of the equation over a time period, say from 0 to t.
Right.
The left side is trivial. The integral of a pure differential just gives you the function evaluated at your starting and ending times.
Easy enough.
But on the right side, we are left staring at a stochastic integral. We have to integrate sigma times e to the gamma s times dx.
And integrating with respect to dx sounds absolutely miserable.
It is.
We already established dx is a jagged, infinite speed nightmare. We do not want that trapped inside an integral.
We absolutely want to avoid it if possible. And to get around this, the source material introduces a technique called stochastic integration by parts.
Oh, I've heard of that.
The goal is to eliminate the dx term from the driving seat of the integral. In this integration by parts formula, we separate our expression into two pieces: a smooth deterministic function, our exponential, and our random Brownian motion, x.
Let me guess how this works. Integration by parts usually involves finding the derivatives of the two pieces. But because our exponential function is perfectly smooth, it has no chaotic variation, right?
That is the key. In stochastic calculus, we track something called quadratic variation, which is essentially the accumulated jitter of a path.
Yeah.
Brownian motion has a quadratic variation equal to time, but a smooth, deterministic exponential function has a quadratic variation of absolute 0.
There is no jitter at all.
None.
So when we combine them in the integration by parts formula, the cross terms, the parts where the two variations interact, they just disappear completely.
Yes. Because the smooth function contributes 0 quadratic variation, the cross bracket term vanishes. And this mathematical clearance allows us to flip the differential.
Flip it how?
Instead of being forced to integrate with respect to the chaotic dx, we shift the burden. We rewrite the equation so we are integrating the random path x with respect to deterministic time, dsc.
Oh, we've mathematically wrestled the chaos into a box that we can actually calculate using standard time.
Exactly. We converted a stochastic integral into a standard Riemann integral over time.
That is incredibly satisfying.
If we step back and look at the bigger picture, This derivation perfectly illustrates the daily workflow of quantitative analysts and applied mathematicians.
They don't fight the chaos.
You don't try to solve chaos head-on. You find structural loopholes, you exploit linearities, and you use integration tricks to transform a chaotic equation into a deterministic one.
I love that. But let's ground this in reality for a second. We've spent all this time mastering a single path, a single particle experiencing friction, a single interest rate.
Right, the 1D model.
But the real world is almost never one isolated line. A financial market isn't just Apple stock. An ecosystem isn't just one species.
Not at all.
What happens when we have multiple jittery variables evolving over time all at once and they are all interacting?
That is when we cross the threshold into the realm of multivariate SDEs. We have to really scale up our mathematical machinery.
Let's define the architecture of a multivariate SDE. If we are dealing with multiple variables, how many independent variables do we have? Do we add multiple dimensions of time?
No, and this is a critical distinction to maintain. A multivariate SDE still has only one independent variable, which is time, t.
The timeline is universal.
Exactly. Yeah. But the dependent variable, the state of the system, is no longer a single number. It is upgraded into a high-dimensional vector.
Let me try a visual analogy for a vector for you listening. Instead of tracking a single line on a graph representing Apple stock, our system state is now a massive spreadsheet column.
I like spreadsheets.
Right. So row 1 is Apple, row 2 is Google, row 3 is Amazon, and so on for maybe 500 different stocks. The vector is that entire column moving through time together.
The spreadsheet column is an excellent way to visualize a vector state, which we denote mathematically as a bold X.
Okay, bold X.
The equation governing this massive column still relies on two main forces, just like our 1D model. First, there is the drift vector.
What does that do?
It determines the deterministic expected trends for every single stock in your column. Basically a column of average expected returns.
Okay, that makes sense. But the real complexity, according to the source material, lives in the second component, the diffusion matrix.
Yes, typically denoted by the Greek letter sigma. In a 1D system, diffusion is just a single number telling you how bouncy that one variable is.
The rattle.
But in a high-dimensional system, you don't just care about how bouncy Apple is in isolation. The diffusion matrix determines how different variables correlate and cross-contaminate each other.
Cross-contaminate. So if Apple takes a random positive shock, the matrix dictates how that shock bleeds over into Google's price.
It dictates the entire web of interconnected shocks. And because of this cross-contamination, the multivariate version of Ito's lemma becomes significantly more complex.
I can imagine.
We can no longer rely on basic calculus. We must borrow heavy machinery from linear algebra, specifically the Hessian matrix, and an operation called the matrix trace.
Hold on, for those of us who haven't taken linear algebra in a decade, what actually is a Hessian matrix? Are we just talking about a spreadsheet of derivatives?
Conceptually, yes. Imagine a grid, but instead of holding prices, this grid holds second derivatives.
Okay.
It is a matrix that captures the curvature of the system in every possible direction.
The curvature.
The diagonal of this grid tracks how each variable accelerates in its own isolated direction. But the off-diagonal elements, say, row 3, column 7, track the mixed second derivatives.
Meaning what?
They measure how a change in variable 3 affects the slope of variable 7.
Oh, so it's an accounting system for how curves interact with other curves.
Exactly.
And why does Ito's lemma need this massive grid?
Because we have to capture what are called second-order cross-terms. Remember our 1D multiplication table? dx squared equals dt.
Right.
But in a multivariate system, what happens when the random shock of variable I multiplies by the random shock of variable k? What is dxi times dxk?
If they were completely independent, you'd think they would just average out to 0.
But they aren't independent. It turns out that cross product is equal to the covariance between those two specific variables multiplied by dt.
Wow.
The math forces us to track the covariance rate matrix of the entire system. And the Hessian matrix is the structural tool we use to multiply all those covariances by their respective curvatures.
I have to ask a foundational question here, one that anyone staring at a 500 by 500 matrix of cross derivatives would ask.
Go for it.
Why go through the nightmare of massive matrices and cross-contamination? If I have 500 stocks, why not just set up 500 isolated 1D equations, solve them separately, and staple the answers together in a folder at the end?
That sounds tempting, right?
Very. Why treat them as a single, giant, tangled vector?
Because stapling them together creates a fundamentally false reality. That is the difference between a decoupled system and a coupled system.
A coupled system.
You cannot separate them because variable A's instantaneous speed directly depends on variable B's current position and vice versa.
Yeah.
They are mathematically entangled.
Give me a tangible example of this coupling in the real world. Why can't I separate them?
Let's look at biology. The most famous example is the Lotka-Volterra predator-prey model.
Okay, I remember this.
Imagine an isolated ecosystem containing only rabbits and foxes.
Rabbits are variable A, foxes are variable B.
If you try to write a differential equation to solve for the rabbit population in absolute isolation, you will fail.
Why?
Because the death rate of the rabbits isn't a static number. It depends entirely on how many foxes are currently alive and hungry.
Right.
And you can't solve for the foxes in isolation either, because their birth rate depends on how many rabbits are available to consume.
So they are completely linked.
The variables are coupled through a multiplication term. The speed of A requires the position of B. The system can only be solved or simulated as a single unified vector evolving together.
So trying to staple isolated answers together is it's like trying to understand a complex argument between two people by locking them in separate soundproof rooms, recording them talking to themselves, and reading the transcripts later.
That is a brilliant analogy.
You completely miss the interaction, which is the entire point of this system.
The interaction is the system. In astrophysics, we see this in the three-body problem.
Oh, sure.
The gravitational pull and trajectory of planet A depends continuously on the constantly moving locations of planets B and C.
And in finance.
In finance, we see it in the Heston model.
The Heston model, that's a famous framework for pricing options, right? How are the variables coupled there?
Well, in the classic Black-Scholes model, volatility, how bouncy a stock is, was assumed to be a constant number.
Which is definitely not true in real life.
Exactly. In reality, volatility changes. So the Heston model treats an asset's price and its volatility as two separate random processes, and they are fiercely coupled.
Oh, so.
The stock price bouncing around is variable A, but the bounciness itself is variable B, which is also randomly wandering over time.
And how do they contaminate each other?
Usually, they are negatively correlated. When a stock price crashes, panic sets in, and the volatility spikes violently.
Right, fear goes up.
The trajectory of the price directly informs the trajectory of the bounciness. You absolutely cannot staple those together after the fact. You must solve them as a coupled matrix.
You know, here's an application that completely blew my mind from our research notes.
What's that?
This exact math, this highly coupled multivariate stochastic calculus, is the engine powering the biggest technological breakthrough of the decade: AI image generation.
Oh, yes. Tools like Stable Diffusion or Mid-Journey.
Yeah.
It is a stunning modern application of the math we are discussing. In a diffusion model, an image is just a massive grid of pixels. Let's say a high-resolution image has 2 million pixels.
Okay.
The AI algorithm treats every single pixel's color value as one variable in a gigantic 2 million dimensional vector.
So our bold X isn't 500 stocks or 2 animals, it's an incomprehensible 2 million interconnected pixels.
Yes. And the AI starts with an image of pure, uncorrelated, random static TV noise.
Right.
It then solves a reverse-time stochastic differential equation to slowly remove the noise, step by step, steering the static toward a recognizable image.
Yeah.
And this process must be heavily coupled.
Why can't I just fix one pixel at a time?
Because the specific color a single pixel should become depends entirely on the colors the pixels immediately next to it are becoming.
Oh, right.
To form an edge or a shadow or the curve of a human eye, the pixels must coordinate. The variables must cross-contaminate each other into coherence.
That's incredible.
The AI is essentially calculating a 2 million dimensional Hessian matrix to reverse the entropy of the image.
We've gone from a single rattling train to an ecosystem of foxes to a universe of 2 million pixels negotiating with each other. It feels like we've hit the ceiling of complexity.
You'd think so.
But the source material pushes us even further. It says vectors aren't enough. We have to look at the infinite canvas.
We must. We've gone from a 1D scalar to a high-dimensional vector, but vectors still represent discrete, countable things: foxes, stocks, individual pixels.
What's the alternative?
What if the subject we are studying isn't made of discrete points? What if our subject is an entire, continuous, unbroken landscape?
Oh, to map a landscape, we must add spatial dimensions.
Exactly. And that leads us to the terrifying world of SPDE's stochastic partial differential equations.
Let's clearly define the architectural shift here. Unlike the SDEs we just talked about, which only have one independent variable, time, SPDEs have multiple independent variables.
Yes, they have time, t, A and D, they have space X.
So instead of tracking a train along a single track of time or even 500 trains on 500 tracks, we are tracking the exact height of every single millimeter of water on the entire continuous surface of an ocean as time moves forward.
Exactly. The state of the system is no longer a single trajectory or a vector of trajectories. The state is a random field evolving in an infinite dimensional space.
That is hard to even picture.
At any single millisecond, the answer isn't a number. It's a completely continuous, undulating, jagged surface.
And the randomness hitting the surface isn't just one shock. The text calls it space-time white noise. What does that actually mean visually?
Think back to our untuned television set showing pure static. That static is random over time. Every single frame is completely different from the last. But it's also completely random over space.
Meaning the pixels are independent.
The pixel in the top left corner is doing something completely independent from the pixel immediately next to it. That is space-time white noise.
Wow.
It is uncorrelated, pure randomness at every microscopic coordinate in space, at every microscopic instant in time.
I'm going to be honest, as a host trying to mentally model this for everyone, this sounds mathematically broken.
It does.
If dx was already destroying classical calculus in one dimension, what happens when space itself is just pure, unadulterated, static noise?
You have right to feel that way. Mathematicians are deeply challenged by it. In the presence of space-time white noise, traditional calculus fails entirely. Even the advanced stochastic calculus we just spent 30 minutes discussing fails.
Wait, why? What breaks?
The math breaks because the noise is so severe, so what mathematicians call singular, that in a classical sense, it doesn't even qualify as mathematical function anymore.
It's not a function.
No. It is so jagged that it has no defined numerical values at specific geometric points. If you point to an exact coordinate and ask for the value, the static oscillates infinitely.
Good grief.
It can only be treated rigorously as a distribution or a generalized function.
So it's like trying to measure the exact perimeter of a rugged coastline, but the rules dictate you have to measure around every single individual grain of sand and every atom inside the sand.
Exactly.
The answer just blows up. It approaches infinity.
That is the exact problem. If you take space-time white noise and plug it directly into a nonlinear equation, the math immediately spits out infinity. It diverges. The equation self-destructs.
So how do you fix an equation that self-destructs?
To even attempt to solve these SPDEs, mathematicians had to invent entirely new, highly abstract frameworks. One of the earlier approaches is using what the text calls mild solutions.
Mild solutions. It sounds like a doctor trying to calm the math down with a sedative.
That's essentially what it is mechanically. They use a concept called heat semigroups.
What is that?
Imagine you have a metal plate with a highly erratic, jagged temperature distribution. Hot spots and cold spots right next to each other.
Okay.
If you let time pass, the heat naturally diffuses, blurring the hot and cold spots together into a smoother gradient.
Right. Nature seeks equilibrium.
A heat semigroup acts as a mathematical blurring tool, converting the harsh, unsolvable differential equations into smoother integral equations that average out the singularities so they can actually be calculated.
So they artificially blur the static just enough to do the math.
Yes. But the text highlights an even bigger, more recent breakthrough. It mentions that a Fields Medal of the Nobel Prize of Mathematics was awarded for figuring out how to solve the absolute worst of these equations without just blurring them.
Oh, wow. Who won that?
Martin Harrer won the Fields Medal for inventing a framework called regularity structures. It is considered one of the great triumphs of modern math.
Break that down for me. If the math spits out infinity, how did he fix it? You can't just subtract infinity from infinity and get a normal number.
Actually, in a highly rigorous algebraic way, that is exactly what he did.
Really?
Yes, it is a process called renormalization. Think of it like trying to listen to a voice recording that is completely overwhelmed by incredibly loud, infinite static.
Okay.
You can't just turn the volume down, because you turn the voice down too.
Okay.
But if you can identify the exact mathematical structure of the static, its frequency fingerprint, you can build a filter that perfectly subtracts that specific infinite noise.
Leaving only the finite, meaningful signal behind.
Exactly.
So he basically invented noise-canceling headphones for pure mathematical chaos.
That's a perfect way to put it. He created an algebraic scaffolding that allows you to isolate the infinities caused by the space-time white noise and subtract them away in a perfectly balanced manner, leaving behind a meaningful, finite mathematical reality.
And what are we using these incredibly complex, infinite-dimensional SBDEs for? Why go through the trouble? The text mentions something called the KPZ equation.
The KPZ equation, named after Kardar, Parisi, and Zhang, models the dynamic growth of interfaces.
Interface.
Think of the leading edge of a raging wildfire spreading through a dry forest, or a crystal rapidly growing in a petri dish, or a bacterial colony expanding.
So a boundary that is moving forward.
Yes, the edge is driven by a predictable outward expansion, but it's constantly perturbed by microscopic, random spatial noise.
Like a sudden gust of wind or a pocket of dry leaves.
Exactly, or the microscopic grain of the petri dish. The KPZ equation captures the exact universal statistical laws of how that jagged edge evolves.
The sources also mention the Navier-Stokes equations, which physicists use to try and model the actual chaos of fluid turbulence, like a rushing river or airflow over a jet wing.
Yes, very important in aerodynamics.
And in finance, there's the HJM model.
The Heath-Gerald-Morton model. Instead of modeling a single interest rate, the HEM model treats the entire yield curve, the interest rates for every possible maturity date into the future, as a continuous, fluctuating string evolving over time under random market shocks.
SPDEs are just the ultimate language for continuous spatial chaos.
They really are. It is the frontier of mathematical physics.
But before we get totally lost in infinite dimensions, the source material wisely hits the brakes.
Yeah, we need to regroup.
It takes a quick step back to point out a massive, very common point of confusion for students and professionals alike regarding the terminology we've been using.
It is necessary to clear this up. We need to do a quick vocabulary check regarding the word multivariate.
Right. Because it means completely different things depending on which floor of the university math department you are standing on.
Very true.
Let's look at the pure math department first, specifically what they call multivariate calculus.
In pure math, the word multivariate is heavily restricted. It means the function has multiple independent variables, multiple independent inputs that you can change freely.
Like plotting a 3D topological map, z equals f of x, y.
Right.
The altitude, z, depends on two completely free inputs, your longitude x and your latitude y. I can change x without changing y. It maps a static surface.
Correct. Multiple inputs, one output. But if you walk down the hall to the differential equations department or the dynamical systems lab, the definition practically flips.
Oh, so?
In their world, a multivariate system means there are multiple dependent variables, multiple outputs or states evolving over only one independent variable.
Which is almost always time.
Exactly.
This brings us back to our massive spreadsheet vector from earlier, 500 stocks evolving over one shared timeline. One input, 500 outputs.
Exactly. So what happens in the differential equations department if you actually do have multiple independent variables, like time, A, and D space?
They don't call it multivariate. They give it a completely different name. It becomes a partial differential equation, or PDE.
Yes. So to summarize the clash simply, in pure math, multi refers to the inputs you control. In differential equations, multi refers to the outputs the system produces.
Let me try to lock this in with an analogy for you listening. In pure math, a multivariate function is like a DJ's mixing board. You have dozens of sliders: bass, treble, synth, volume. You can independently push any slider up or down without affecting the others. Multiple independent inputs controlling one final output sound.
I like the mechanics of that. Multiple independent inputs. And how would you describe the differential equations definition?
A multivariate differential equation is like hitting a single play button on a sequencer. The play button is time passing. That is your single independent variable.
Right.
But hitting that one button triggers a whole orchestra of different digital instruments to play their individual interacting tracks simultaneously. Multiple dependent outputs evolving from a single moving input.
That's a phenomenal analogy.
Yeah.
You have the DJ board versus the play button.
Glad it works.
And to be mathematically rigorous, when differential equations people talk about that orchestra of outputs, the strict formal name for that is a vector-valued function, or a mapping. It takes one input, time, and maps it to a high-dimensional vector space.
Okay, so understanding how all these variables, whether inputs or outputs, link together, brings us to the ultimate accounting tool in calculus. Yes.
It's how we track the ripple effects when variables are actually constrained by the physical reality of the world. The source text brings up the chain rule.
The chain rule is what I like to call the full pathway tracker. It is how we calculate change when variables are no longer allowed to be completely independent abstractions.
Unpack that. What do you mean by no longer independent? In pure math, the x-axis and y-axis are perfectly independent. They are orthogonal. Moving right doesn't force you to move up.
In the abstract realm of a blank graph, yes. But in physical applications, variables are almost always bound by constraints.
Can you give an example?
Let's use your topographical map again.
Mm.
You have a function representing the temperature z at any point on a landscape, z equals f of x, y. In pure math, you can magically test the temperature anywhere. But what if there is a bug walking across that landscape?
The bug's x and y coordinates aren't independent anymore. They both depend on a deeper variable, the time t that the bug has been walking. Precisely. Or imagine a hiker on a mountain. Their altitude z depends on their map coordinates x and y, but the hiker is physically constrained to a specific marked trail.
They can't just wander off.
Mathematically, that trail is a constraint equation, say phi of x, y equals 0. They can't just step off the trail into thin air to test a new x without a new y. Because of the trail, x and y are secretly locked together.
So the question becomes, how do we calculate the total rate of change? How do we find out how fast the bug's temperature is rising or how fast the hiker's altitude is changing if every step in x inherently forces a step in y?
We use the total derivative, which is powered by the chain rule. It forces you to account for every possible path that a change in the root-independent variable can take to affect the final output. It calculates the total transmission of effect.
Walk us through the mechanics of those pathways. How do we sum them up?
There are usually two channels we must track. First, the direct explicit channel. Let's look at the bug. How does the passage of time directly affect the bug's x position? And then, how does that x position affect the temperature z? We mathematically map that explicit path, t to x to z.
We calculate that by multiplying the bug speed in the x direction by the temperature gradient in the x direction.
Correct, but we are only halfway done. We must add the indirect implicit channel.
Which is the as path.
Exactly. We have to ask, how does time affect the bug's I position? And how does that y position affect the temperature z? We map t to y to z, calculate that product, and physically add it to the first channel.
Right.
By summing all explicit and implicit channels, we find the true total rate of change.
I really like this framing. So taking a regular partial derivative is like asking a hypothetical question. How does the car move if I only turn the steering wheel and magically freeze the gas pedal?
Yes.
It's an isolated vacuum. But the total derivative acknowledges reality. It says, turning the steering wheel physically shifts your body weight, which inherently causes your foot to press harder on the gas pedal. We need to track that entire interconnected chain reaction.
That captures the essence perfectly. It tracks the reality of the system. In modern mathematics, we unify all of these branching pathways using a master switchboard from linear algebra called the Jacobian matrix.
A master switchboard. I like that. What does the Jacobian do?
Whether you are in 1D, 2D, or a 100-dimensional vector space, the chain rule is fundamentally just multiplying Jacobian matrices together. The Jacobian is a grid that houses every single partial derivative of every single variable.
Wow.
When you multiply them, the matrix math automatically routes the explicit and implicit pathways, multiplies the correct rates, and sums them up perfectly. It is the ultimate router for calculus.
The text also mentions a concept related to this called the invariance of differential forms. That sounds like a rule of magic. What does it mean?
It is incredibly powerful for mathematicians. It means that the equation for a total differential, typically written as dz equals fx dx plus phi phi dni, stays structurally identical, regardless of whatever deeper hidden variables x and y might secretly depend on. Even if x and y depend on time or temperature or a complex web of other factors, that top-level equation never changes its form. It acts as a universal adapter for calculus. You can plug it into any coordinate system and it holds true.
A universal adapter. But here is the critical question.
Right?
Does that adapter still work when we plug it into the pure chaos of stochastic calculus? This brings us to the climax of the source material, the moment where classical math truly breaks, the death of the derivative.
This is where everything we've built up to mathematically shatters. We established earlier that in classic differential equations, you can easily freely swap between forms.
Right.
You can write an equation in derivative form, focusing on speed, like d over dx equals something. Or you can multiply both sides by dx and write it in total differential form, focusing on increments. D's equals something times dx. They are mathematically identical.
Because velocity, the derivative, and a tiny step forward, the differential, are just two sides of the same coin when the curve is smooth.
But what happens to the concept of the derivative when we plunge it into the stochastic world? What happens when we try to swap forms in a stochastic differential equation?
The source material is violently clear on this. It says this conversion is strictly illegal.
Very illegal.
You absolutely cannot write df over dt or dx over dt in stochastic calculus. It is a mathematical sin.
And we know exactly why now. Because of the microscopic battle we unpacked earlier.
The variation scale.
We proved mathematically that the random step dx scales with the square root of times square root of dt. So writing dx over dt is essentially trying to divide the square root of dt by dt.
Which algebraically simplifies to 1 divided by the square root of dt.
And as dt shrinks to 0?
The denominator of that fraction becomes 0, and any number divided by 0 explodes to infinity.
Exactly. As the time increment approaches 0, the instantaneous velocity approaches infinity. The very concept of a derivative, the idea of measurable, instantaneous speed at a specific point in time, completely and utterly shatters. It ceases to exist.
Because the path is so jagged, so fractal, that if you freeze time, the particle isn't sitting still. The math says it's effectively vibrating at infinite speed.
Therefore, random FDEs can only be written in total differential form. df equals a dt term plus a dx term. You can never divide by dt.
Wow.
The differential form is actually just a shorthand notation. What it really represents is a stochastic integral equation. We have to completely abandon derivatives and take refuge in integrals because integrals smooth things out by summing up the chaos over a defined period of time.
Okay, I have to ask the obvious practical question for you listening. If quantitative analysts on Wall Street and physicists in labs can't use derivatives to find the rate of change of an asset or a particle, how do they actually build anything? How do you engineer a system or price an options contract if the foundational math says speed doesn't exist? How do you calculus without speed?
It is a profound engineering problem, and the workaround they developed is just a masterpiece of applied mathematics.
What's the workaround?
Since they cannot take a strict, instantaneous derivative, they use a philosophical workaround involving infinitesimal generators and the concept of conditional expectation.
Break the mechanics of that down for me. How does taking an expectation and average fix the infinite speed problem?
Let's look at our SDE. We have a deterministic dt term and a chaotic dx term. You know the dx part is causing the infinity problem because it represents pure, unadulterated randomness.
Right.
But what is the average or expected value of pure, unbiased randomness over time?
Well, if it's truly unbiased, like flipping a fair coin a million times, the positive shocks and the negative shocks should perfectly cancel each other out.
Exactly.
The average is exactly 0.
Precisely. The expected value of Brownian motion is 0. So instead of trying to solve the chaotic equation directly, mathematicians apply a conditional expectation operator to the entire equation.
They ask, what is the expected average path of this system?
By doing so, the chaotic noise term is mathematically erased. It averages out to 0.
So it's not that the chaos magically disappears. It's that over a long enough timeline or across enough parallel realities, the lefts and rights cancel out and you are left with the underlying trend.
And what happens when the dx term is gone? You are left with only smooth, deterministic terms, the dt terms. And once the infinite dx is gone, you are finally allowed to divide by dt again.
Oh.
You have successfully transformed a chaotic, unsolvable, stochastic differential equation into a smooth, completely predictable partial differential equation.
You essentially zoom out until the jagged line looks blurry enough to draw a tangent line on it.
It is exactly what Fisher Black and Myron Scholes did to win the Nobel Prize in economics.
Really?
This exact philosophical workaround is the bedrock of the Black-Scholes option pricing model. They took the unmeasurable chaos of market risk, specifically what traders call gamma risk, the curvature, and theta risk, the decay over time caused by dx.
Right.
And they mathematically translated them into a deterministic PDE. That PDE spits out a clean, exact, finite price for an options contract.
They didn't solve the chaos, they built a mathematical bridge over it. That is incredible. And this brings us to the final concept from our source material.
Yes, the final showdown.
To wrap up all these ideas, the text asks us to look at the ultimate distinction in calculus. It asks, are the words differentiable and derivable the same thing?
To a high school calculus student, those words are completely interchangeable. But to a stochastic mathematician, they describe entirely different universes.
Let's trace the evolution of these two words to see how they split. Let's start with the basics. 1D classic calculus, Newton's world.
In 1D classic calculus, they are identical. If a function is derivable, meaning a local slope or measurable speed exists, then it is also differentiable, meaning a local linear approximation exists.
You have a slope, therefore you can draw a straight tangent line. The concepts are locked together.
Simple enough? What about when we scale up to multi-D classic calculus?
Right, multidimensional space.
Here, a split begins. In multidimensional calculus, being differentiable is a much higher, much stricter standard. Derivable just means that the partial derivatives exist.
Meaning what, visually?
It means if you stand at a crossroads on a mountain, you can pull out your tools and measure the exact slope looking perfectly north and the exact slope looking perfectly east.
But the text says that's not enough to be considered differentiable. Why?
Because differentiable means a perfect 360-degree flat tangent plane exists globally at that point.
Yeah.
You could have defined slopes north and east, meaning it is derivable, but there could be a jagged, broken cliff face hidden in the northeast direction between your axes.
Ah.
That hidden cliff means you cannot place a flat piece of glass on that point. It is derivable, but not differentiable.
Okay, so differentiable is the absolute gold standard of smooth approximation. Now, the final boss, stochastic calculus. What happens to these two words when we expose them to the infinite vibration of Brownian motion?
This is the ultimate violent split. As we just discussed, derivability is utterly dead.
Because Brownian motion has no defined instantaneous speed.
Exactly. The derivative does not exist. The function is strictly, permanently non-derivable.
But does differentiability somehow survive?
It barely survives.
Yeah.
It hangs on by a mathematical thread, and it is entirely rescued by Ito's lemma. Remember that second-order correction term we talked about, the one that required the second derivative?
The term that captured the squared randomness, dx squared, and turned it into deterministic time?
Yes. In classical math, differentiability relies on drawing a straight, flat, tangent plane.
Mm-hmm.
In stochastic math, we can't draw a flat plane.
Right, because of the chaos.
But because we include that quadratic variation term, because we track the curvature, we are able to mathematically approximate the incremental changes of the function using a curved surface.
Wow.
We can write a valid df equation. So the system is technically differentiable in the stochastic sense because we can approximate its next step, even though it has absolutely zero derivability.
I am marveling at the architecture of this. Let me try to summarize this distinction using a physical analogy.
Report.
Derivability demands that you can measure a clean, precise speed. Randomness completely destroys speed, so derivability dies.
Right.
But differentiability just asks for a way to build a bridge to the next incremental step. Classical calculus assumes the ground is smooth glass, so a flat board works.
Yes.
Stochastic calculus realizes the ground is actually a jagged chain-link fence. Ito's lemma is the mathematical duct tape and plywood that spans the gaps in the fence, making the estimation possible. It patches the holes left by the infinite speed of chaos.
Duct tape over a chain link fence. That perfectly describes the utility of Ito's lemma. Stochastic calculus is a world composed of integrals and differentials only. It survives because human beings engineered a nonlinear, second-order form of approximation to navigate a universe where instantaneous speed is infinite.
Let's take a breath and recap this incredible journey for you listening. We started with what looked like a deceptively simple 1D random equation, the Ornstein-Uhlenbeck process.
And we zoomed in to uncover a microscopic paradox. The fact that random steps, RDX, actually scale larger and move infinitely faster than the flow of time, dt.
Which fundamentally broke classical calculus and forced us to rewrite the multiplication tables, proving mathematically that pure chaos, when squared, equals predictable time.
We then explored how these variables cross-contaminate each other. We looked at multidimensional vectors using Hessian matrices to track covariances, powering everything from predator-prey models to AI image diffusion.
And then we scaled up to the infinite, continuous landscapes of SBDEs, looking at how regularity structures act like noise-canceling headphones for space-time white noise.
Then finally, we witnessed the death of the derivative. We saw how pure randomness destroys the concept of measurable speed, forcing quants and physicists to use expected values and infinitesimal generators to build a bridge over the chaos, entirely redefining what it means for a system to be differentiable.
Today we learned that to mathematically tame true randomness, human beings had to completely sacrifice our classical intuitive understanding of speed and derivatives.
Which leaves us with a fascinating, almost provocative thought to ponder as we close.
What's that?
If our financial markets, our turbulent weather systems, and the microscopic physics of our universe are fundamentally ruled by stochastic equations where instantaneous velocity is an absolute mathematical illusion,
Yeah.
how much of our everyday human intuition about cause, effect, and speed is fundamentally flawed when exposed to the true, unyielding chaos of the real world?
That is a question to keep you up at night. Are we all just pretending the jagged lines are smooth? Thank you so much for joining us on this deep dive into the mathematical architecture of chaos. Keep questioning the hidden math behind reality, and we'll see you next time.